Now starting. All attendees are in listen-only mode.
Good morning, everybody, and welcome to this second webinar of today for iMachining. My name is Les Boland. I'm one of the technical support engineers here at SolidCAM in Barnsley. And this webinar is going to be covering the 3D flavour of iMachining. Earlier on we did the 2D version, if any of you were also attending that webinar. And in that webinar we learned all about how iMachining is uses intelligent control stepovers and morphing spirals, etc., to create its unique toolpath. And in this webinar we will be seeing how we also can use the same strategy in a 3D machining environment, and also a separation of various areas and what have you, to create less air cutting and a more streamlined and efficient toolpath. So moving on from this morning's webinar, having covered the initial toolpath and the approach to it, if we've got a slide show, let me just check that you can see what I'm seeing. Yes, you can. We've got the slideshow here. I'll continue with that, and we've got exact stock machining. As I mentioned earlier, the iMachining engine knows where the stock is all the time, and this is more important when doing the 3D iMachining, because obviously on a 3D model we need to know where our stock is, and it can be quite a complex stock shape as well. So the stock model is important that it's accurate, and then we're going to minimize our air cutting time, or do away with it completely indeed. Okay, so our next slide here is showing two of the features that we find in iMachining, and only iMachining. There's various other manufacturers, software manufacturers out there, CAM manufacturers, that purport to do something that is like iMachining, but these is where the similarities end. There's the morphing spirals, which is the shape-changing spirals that are unique to iMachining and not available in any other system. And this is what gives it the edge, really, is the ability to change shape and be sympathetic to the cutter and the machine at the same time. Also, we have separating of different areas within the iMachining. It does it automatically. So if it sees an area, it's better seen in the 3D environment than the 2D, although it does do it in the 2D, but it separates various areas out. It'll go at one area first, attack that area, so that it can ramp up to its maximum feed in one area before it has to jump over into a separate area and then machine that separate. Okay, so what that means is, in iMachining you get less retracts. It stays more in contact with the material, because it doesn't have to hop from one side to another each time. You get a smoother motion, and therefore your machine runs faster. With the other similar types of machining, intelligent machining of this type, such as the volume mill, you do not get this. You do not get the morphing spirals, etc. So you get more repositions and more re-entries and exits, etc., etc., etc. But you can compare it like for like. But as far as I'm aware, no other company does the morphing spirals, etc. that we do. And we've got this little graphic here where intelligent separation. Basically, if you've got any islands in the part, you're able to use the iMachining feature to get around them quite easily. It does it automatically. It says conquer islands there. I don't know what it means, that you're some sort of swashbuckling hero, but you're able to just use any geometry that has islands, and the iMachining engine will calculate itself its best toolpath. You can form spirals on any geometry, machine areas that's got the most material to remove first, and that's pretty much its key strategy. What it does, it sees the area that's got the most material on it to remove, and it goes at it first, because it uses a longer flute length than you traditionally would use in your machining. You know, you may when you're traditionally trying to program something, you have to give it a step down value, your tool. So you may say, well, I don't really want to take more than 5 milli a time off, you know, we best be careful, or whatever it is, you know. So you'll choose your depth of cut, and of course it's a constant depth of cut, so each time you do a step down it's 5 milli, 5 milli, 5 milli, so you're wearing away the 5 millimeters of the end of your tool all the time. So you'll end up regrinding your tool, so you lose that last 5 millimeters of your tool, and you've got yourself a new tool but shorter. Well, SolidCAM sort of eliminates that, because it varies the length that it cuts on. It'll cut at the maximum depth of cut that it sees is, or it considers or calculates is correct for that machine, that tool, that material. But on a 3D part especially, you'll use your maximum length of flute length that it can when it's removing the material. But then when it's machining closer to form, when it's stepping up, traditionally you would step down at a certain depth, but because iMachining works backwards, it does the depth first, then it'll step up. So it uses the maximum depth of cut before it has to use the smaller depth of cut. So I call them step ups. And so that varies each time, depending on the shape of the geometry. We'll see this when I demonstrate the geometry. So the variation of depth of cut, varies according to the shape of the model. You'll see this as and of course with the intelligent engine that's behind iMachining, you're going to also save your programming time, because you don't have to tell it what to do. It works it out for you. Okay, so with that, we need to know, well, how do we do it already? What do we do at the moment when we're creating a program? How do we choose our feeds and our speeds? Well, at the moment, we do like anybody else would. You use your either your past experience, you know, this is how we've always done it, you know, this material, this tool, we've always done it this way, this is how I know that this is my feed and speeds that I use, I know it's alright. You might use trial and error. You might think, well, we'll chuck a feed rate at this tool, and hopefully it won't bust, and if it does, then you think, well, we'll knock it down a bit then. That's another way of getting your feeds and speeds. And another way is reading out of the manufacturer's catalogues. Of course, you pick a nice new tool from Iscar or Kenner Metal or Sandvik or whoever. You read their data, and you say, okay, that's my recommended feed and speeds. From there, I'm gonna go at it. Or you might get a rep in or whatever, and they'll give you their recommended speeds and feeds, and then you'll probably find that you've got to knock it down a bit as well, because they're always at the optimum, them, from my experience, them speeds and feeds. So currently you choose your feeds and speeds from one of, or a variation of them three methods. But in SolidCAM, iMachining rather, SolidCAM iMachining, what you have is a proven technology wizard, which has been trialed on various machines, various materials and various tool types, to get an optimum speed and feed and step over for your given material. So it's in the machine and material database, and it synchronizes the information from the three parameters, which are your material, your machine, and your tool, your tool style and material, etc. And it just calculates out the best speeds and feeds for you. But as I mentioned in the previous webinar, you do have control over this. You don't have to just go with what it says and then that's it. You know, if you get it on the machine and you think to yourself, well, actually, I think that could go a little bit faster, then you can change your value on your slider, on your brave meter that I call it, and increase your feeds and speeds proportionally to as to where you think it should be. Okay, so that's what it's all about. Let's just do that on a model here. What I've got is a simple little mold tool, it looks like, doesn't it? And I know you would normally use a tool steel, I don't know, in EN19, EN24 type of steel, maybe, I don't know, something even harder than that, like a D2 or something, steel for a mold. But for this demonstration, this particular part is made out of aluminium. So you might think that's a cop-out to use aluminium for an iMachining demo, but it demonstrates on here quite nicely the depth of cut that it's quite happy to machine at. Also, for demonstration purposes, it's easier to simulate quickly something that's being cut out of an easy to machine material. But rest assured, you know, it's just as efficient with the tougher materials as it is with the simpler materials. In fact, I think it's better with the tougher materials because aluminium is notoriously can be notoriously difficult to machine sometimes. It might be easy to actually, you know, nice and soft, but sometimes it can clog your tool up and all sorts. So I don't like machining aluminium, to be honest. Anyway, here we go. So what we've done here is we've taken our model, which is let's say a nice mold. It's in coming from some rectangular billet there, and as we would do normally in any 3D machining operation, we just show it the complete job and say, yeah, go and machine that for me, please. So I'll just open up the technology and we can see what's under the bonnet, so to speak, with the iMachining 3D. And we only have one option of what iMachining 3D is, and that is 3D surfacing. I understand there is further development going on in there to be doing the finishing, etc. But at the moment, it's as I've said previously, it is a fantastically well thought out roughing strategy is iMachining. It's for stock removal, and that is the way you should be thinking of it. Is if you've got lots of stock like these on this part here, if you've got lots of stock to get rid of, then iMachining is something you should be looking at, because it is fantastically efficient at quickly removing loads of material. Okay, so what we're telling it to do here is we're telling it to look at the whole of that model as its area of interest, and it's going to come at it from directly from above. So anything that it can see directly from above it's going to go at. Our tool in this case is a wait for it to pop up, is a 6mm diameter end mill. It's not the bigger part, is this 6mm diameter end mill with a cutting length of 25 millimeters. The levels is just the upper and lower level of the part, but the technology wizard is where it's all going on. So here's our technology wizard, and there's the brave meter, our slider. Where's my cursor gone? The slider that I was talking about. That changes the aggressiveness of the chips. We've got it on the default setting of 3 for this example, and what it's decided, because the wizard is on, as you can see up here, we've told it to calculate it automatically, which is the whole point of iMachining. The idea is that you let it do its own thing, and it's calculated that it only needs one roughing step down of the maximum depth of 15.695 that you've got there. The The ACP, that's the actual contact point of the tool, is a good value there because of the flute length and the amount amount of flutes. It knows that at any one time there's going to be more than one flute in contact with the material at any one time, which reduces the vibration, any vibration that's likely to happen with the part. You can often have silent running, almost silent running with some of these iMachining parts, because the tool is in engagement constantly, and also because the step down is at such a longer length than you normally would use yourself, your tool supports itself better because it's being supported against the material. So the length that you're sticking out from your holder to your cutting length is a lot shorter than normal. So it's a lot more stable. It goes against pretty much everything you've ever learned about machining generally, because when you look at it you think, well, I wasn't taught that way, but it is very good. Technology similar to the previous example in 2.5D, but this time we've got a little bit more information here where, because it's a 3D part and we're going to step down in big steps, we want obviously to get closer to form. So you can tell it here to do the rest roughing operation. You can either do it now or not do it. That's the option. But if you are going to do it within the operation, you can control that. You can say to it, well, I'd like you to use a scallop value of a certain height. So you can tell it exactly how close to form you want it to be before you do your semi-finishing and your finishing operations. What I've chosen here is a scallop tolerance of 30% of the tool, and you can tell it when you want it to do it. Do you want to do each step down and then rest rough, or do you want to do all the roughing down steps first and then rest rough it? It's up to you. It depends on the shape of the job, to be honest with you, which one you would use there. So okay, but that's all we've needed to do. You tell it to go at it, then you tell it how you want it to do the rest roughing, and that's it. So I'll quickly look at the toolpath that has been generated there by clicking on there, and you'll see quite a neat toolpath there on this 3D model. You can see exactly where it's going to be concentrating its toolpath, and you can also see the approaches and retracts from the outside of the model. So let's have a simulate that and see what exactly that means. Now this simulation, because it's a 3D part, it can take a little bit of time, but the reason I've chosen this as well, the each step down and then rest rough, is so that you'll be able to see as it separates different areas out on the model. You'll see that it'll rough it out to depth and then do the step ups, as I call it. It says step downs, but I call them step ups because that is what it does. You'll see it do the step ups on each area that it's being machined as it goes along. Okay, so we'll hit simulation. Oh, okay. I didn't realise it wasn't calculated. I don't know. I don't think I've particularly changed anything there. Let's just see. So it's calculating the whole toolpath for this model. I was trying to avoid this, but I must have changed something I didn't realise. Doesn't make for very good television, does it? Talk amongst yourselves. Nearly done. And it's just generating the toolpath preview that we saw earlier. Okay, we're happy. We're happy. So this is our model. I'll do it in the host CAD situation first, because it does do that a bit quicker than the solid verification. So if we quickly start it going by just putting it in the single step mode at the moment. You see it's gone straight down to its full depth. It's folding off the side there slightly, and it's gone down to the depth that it's going to approach for that area there. Excuse me for fiddling around with the model, but I just wanted to show you that there. So I'm going to set this going, and you'll see the area that it's concentrating on at the moment. It's going nice and slowly. It's arcing in there nice and slowly, well, not slowly, but nice and gently, and it's creating an area for itself to machine into. I'll just increase the speed slightly there, and you get an idea as to what it's doing. I shall change this to above. Oops, I should have checked what that was beforehand. You'll see that it's arcing in there into that area of interest. That's the first area that it's going to be attacking. It's already predefined that by looking at the shape of the model and deciding which is the first area of attack. You do have control over this, by the way. You don't have to always go with what it's decided. You can tell it to start at a particular area if you need to. And now you can see it's changing the shape now to suit the shape of the model. It's stepping itself up slightly now. It started down at the bottom, but because of the proximity of the shape of the mold there, it's had to step up. This is why I mean by step ups. They are normally step downs, but SolidCAM, I mean iMachining does a step up. So it's always cutting at the maximum depth of cut that it possibly can, which is better for the tool, and it is better for rapid material removal rate. And as you can see now, it's changing shape once again due to the shape of the model, due to the amount of material that needs to be cut off. Okay, what I'm going to do now, and I do apologise for moving the model around, I know it makes you feel seasick sometimes. I'm going to increase the speed of the simulation just so you can get an idea as to what it's doing. It's come around the outside now. It's removing all that material on the outside and then ramping its feed and speed right up as much as it can once it's in that area, and it works its way around from one side to another. There's obviously a little boss sticking up there that it's got to work its way around, so it'll remove all the material at the deepest cut depth that it possibly can. It works its way around there, and then when it's gone round there, it's got the little island in the middle which is been left because of that little upstand there, and then it'll attack that at the end and get rid of that excess material on the top of there. So you can see as it gets close to the form of the shape of the mold, there it is, it's doing that island now, as I said. As it gets closer to the shape of the mold, it's doing its step ups now, and it works that all out by itself based on the information that you've given it regarding your scallops, etc. So it's finishing that bit off, getting right into the corners there, getting closer to form, and once it's finished that area, it'll pick on another area. It's going to get rid of that little pocket there that's inside that little area there, working its way there. It's finished with that now. It's going to attack a little area over here that it needs to clear, and then it'll move on to the next area. So this is what I mean by area separation. It'll choose one area and get that sorted before moving on to the next. So you've got minimal jumping about, you've got minimum retract. It's not hopping from one side of the part to the other constantly and cutting air. It knows where the stock is at all times. Right, I'm just going to really ramp this up now because we can see you can see exactly what it's doing. And this is just a mirror image of what was done on the right hand side, and it's finishing up now, just tucking them corners in and working its way around to the other side and getting rid of all that excess material there. Nearly done. and it's doing the top little bit of material as well, which you may not do that in reality, in real life. You may have flicked that top or across there with a face mill before you've done this to get them levels. But either which way, iMachining is a very efficient way at removing that stock. Now, this will be meaningless to you because it's not your part. You don't know how big it is or whatever, but it's done that in 8 minutes of machining time. Completely meaningless. But what I will show you is something rather quickly like this. It means recalculating the part. So once again, I apologise for the boring television. But if we go into the technology wizard, and this is where it's important to understand what the slider of the machining level actually means. That's the default level of 3, which is what you would do when you very first put a part on the machine and you don't really know much about iMachining. You go about it a bit gingerly and think, well, I'll have it on 3, you know, to see how it goes. But once you see how it goes nice and quickly and how stable it is on the machine, as long as you've got your job clamped really well, you know, and it's not going to go anywhere, you can quite comfortably turn that right up to the top machining level of 8, and I'll just save and calculate that, and you'll see what a huge difference that can mean to the machining time. The aggressiveness of the tool engaging with the part, as it ramps in there, it can engage with the material at a larger angle, meaning that your chip control is going to be a more aggressive cut, and it will just go at it with a bit more gusto. It's almost calculated. Just looking at the toolpath preview again, and I'm going to simulate this on full whack, so that because you know it's going to do exactly the same thing. It's just going to do it a bit more aggressively, and in it goes. It does the same thing. Same step over, same step up, everything. Sorry, not the same step over. The step over is more aggressive because of the aggressive chip control, but the same step up values, etc. So it's the same close to form as it was in the previous operation, but and this again, the time is meaningless. But what we're doing is we're comparing it with the previous time, so you can see how important it is to get that value correct. And you know, if you've got 100 of these to do, then it's going to make a huge difference to the amount of time that you save. And almost done. And we've whacked that down to 3 minutes and 18 seconds. So you can see that's a huge difference in time. So it is, as I say, it is important, although meaningless to you, me, and everybody else who sees this. But it's a comparison of time and how it can be affected by that meter there. Okay, that is pretty much it for 3D iMachining today. This is just a little taster of what can and can't be done. What can be done is ease of programming. I mean, all I've done is told that to look at that model with that tool, and off you go, mate. And it's going at it. Very little programming input from myself there, but you've got a very complex toolpath within 30 seconds of hitting the calculate button. So not a great deal to go to do for the operator, for the programmer, and you've got a fantastically efficient toolpath out of it. So if you do have any further questions regarding either the 2D iMachining or 3D iMachining, please contact us, speak to Alex or email Alex at alex@solidcamuk.com, and or if you do have any further questions, or you would like a personal demonstration on your own part, then we can arrange that for you. Okay. And thank you very much for attending, and I'll see you at the next webinar. Thank you very much. Bye bye.